A hand that weighs less than a can of soda just lifted 20 kilograms. Not a hydraulic claw bolted to a factory rig. Not one of those industrial grippers that only work inside a perfectly staged demo. A hand. 5 fingers, human-shaped, and it weighs 383 grams, about the weight of 6 eggs, and it can hoist a load heavy enough to make most people brace their back before they'd even try picking it up off the floor themselves. That's the part that sounds fake at first. If you've watched robotics videos for any length of time, you've probably learned to expect 2 kinds of lies. The first is the polished demo lie, where a robot does one impressive thing exactly once, under perfect lighting, with 6 engineers standing just out of frame. The second is the spec sheet lie, where a company throws around words like AI, dexterous, and biomimetic, when what they actually mean is that the machine can open and close its fingers in a way that looks convincing for 8 seconds on social media. This story is different from both, because the numbers check out, the engineering is real, and the strangest part is that the company behind it wasn't originally trying to win a humanoid robot arms race. They were trying to solve something a lot more personal first. They were trying to give people a hand back. Once you know that, the rest of the story makes a lot more sense. The hand is called the BrainCo Revo 2, officially a bionic dexterous hand built for robot integration and research. Unofficially, it's the kind of product that makes people in robotics lean forward and ask an uncomfortable question. If this already exists, what's the rest of the humanoid industry about to become? According to BrainCo's published specs and launch materials, the Revo 2 weighs 383 grams, stands 160 millimeters tall, has 11 total degrees of freedom across 6 active joints, delivers at least 50 newtons of full fist grip force and 15 newtons of pinch force, and can handle a payload of at least 20 kilograms. The Pro and Touch versions add EtherCAT support alongside RS-485 and CAN-FD, and the Touch model has a fingertip tactile module that can read pressure, hardness, texture, force direction, and even proximity as it approaches an object. None of that is abstract marketing. It's a specific stack of capabilities packed into something roughly the size of an actual human hand. If you're not an engineer, those numbers might slide right past you, so here's what they actually mean. The hand is compact enough to fit where a human hand belongs. It's light enough that it doesn't drag on the end of a robot arm like dead weight. It's fast, completing flexion and extension in under 0.65 seconds. It's quiet too, staying under 50 decibels at 50 centimeters, which is quieter than a lot of office noise. It has built-in protection against current spikes, stalls, overheating, and collisions. This isn't a cool hand sitting in a display case. It's built to be mounted, tested, programmed, and used. But the number that should really make you stop isn't the weight, or the dimensions, or even the 20-kilogram payload on its own. It's the ratio. Grip to weight comes out to 52.6, meaning this hand can lift more than 50 times its own body weight. Sit with that for a second. This isn't some huge actuator hidden inside a forearm the size of a fire extinguisher. It's a hand small enough to look familiar, light enough to feel almost like a toy in your palm, and yet it performs at a level where it stops being a gadget and starts becoming infrastructure. Most robot hands end up oversized, stiff, or just ugly because engineers usually have to choose. You can build light, or you can build strong, but getting both into a compact, human-shaped form is rare. BrainCo's whole pitch with Revo 2 is that they solved enough of that trade-off to force the rest of the field to pay attention. Raw strength alone wouldn't be enough to matter this much, though that's the trap people fall into with robotics. They assume the hard problem is power, and it almost never is. Power is easy to make ugly. You can build a gripper that crushes things. Warehouses have had brute force end effectors for years, machines that slam shut on a cardboard box, or yank an object off a conveyor belt and look impressive doing it because they're tearing something apart. None of that is difficult. The hard part is control. It's intelligence expressed through contact, touching the world without wrecking it. It's picking up an egg, a paper cup, a shirt sleeve, a cable connector, a screwdriver, a pill bottle, a key lying flat on a table, or the edge of a blanket, and not just grasping the object, but figuring out what kind of thing it is while you're doing it. That's where Revo 2 stops being a weightlifting trick. BrainCo says the touch version has multimodal fingertip tactile sensing, and in its launch materials, the company describes it as able to detect pressure, hardness, texture, force direction, and proximity at the fingertip. In plain terms, the hand doesn't just close around an object, it gathers information the entire time it's closing. It can sense before contact happens and adjust during it. It reacts to slip. It tells the difference between something fragile and something rigid, making the kind of tiny corrections a human hand makes without thinking. When you pick up a full mug of coffee, your grip is constantly adjusting. When your phone starts sliding out of your hand, your fingers tighten and reposition on reflex. When you pick up a ripe peach, you're not running a calculation, you're feeling your way through it. That's the territory robotics has struggled with for decades, and it's exactly where tactile sensing is supposed to open things up. Tactile systems aren't free, either. They cost weight, add complexity, complicate integration, and create durability headaches. BrainCo says tactile functionality typically adds about 30% more weight, so the real trick here wasn't just bolting sensors onto a hand and calling it advanced. It was keeping the hand light while adding perception on top. The company points to advances in materials, transmission efficiency, sensor integration, and what it calls biomimetic joint optimization. The team wasn't only asking how to make the hand stronger, they were asking how to route force, structure motion, and embed sensing so a small machine could act like a much smarter one. This is where the story gets bigger than one product. Zoom out and dexterous hands aren't a side quest in humanoid robotics, they're the bottleneck. They're what decides whether a walking machine turns into a real worker or stays an expensive costume. BrainCo claims dexterous hands account for nearly half the engineering complexity in a humanoid robot, and that's not just company talk. In 2026, the BBC quoted Robotics founder Bren Pierce, saying he thinks the hand is the hardest, most complex part of any humanoid robot, while University of Bristol robotics professor Nathan Lapora pointed to durable tactile capability as one of the field's long-standing unsolved problems. Elon Musk, speaking publicly in 2025, also called the hand one of the 3 hardest problems in humanoid robotics. Startups, researchers, and giant companies all seem to agree on this point. Walking gets the headlines, but hands decide whether the thing is actually useful. Once you hear that, a lot of flashy robot demos start to look different. Backflips are great for headlines. Dancing goes viral. Perfectly scripted movement down a controlled warehouse aisle looks nice on camera. Now put a house key on a kitchen counter. Put a wrinkled shirt in a laundry basket. Put a kid's toy half wedged under a couch. A slippery bottle in a fridge door. A fork in a dish rack. A charging cable on a nightstand. Ask the robot to gently guide an elderly person's arm through a cardigan sleeve. That's when the illusion falls apart and you find out whether the robot has a hand or just an ending. That's the gap between a machine that can move and a machine that can actually function in a space built for people. And human space really is the whole point. Everything around you was designed for hands like yours. Door handles, drawers, faucets, cutlery, light switches, jars, toothbrushes, remotes, mops, keyboards, screwdrivers, clothing, medicine packaging, shopping bags, zip ties, plugs, cords, seatbelts, shoelaces, cups, books, buttons, zippers. The world isn't just visible to us, it's built around finger geometry, grip strength, compliance, and touch feedback. A humanoid robot doesn't become useful just because it thinks better. It becomes useful when it can physically join a world designed around human hands. Which is why the most important part of this story isn't the 20 kilograms, it's where this hand came from. BrainCo didn't stumble into embodied AI because it's trendy. The company built its name in brain-computer interfaces and assistive devices, including prosthetic hands for people with limb loss, and that history matters because the priorities in prosthetics are nothing like the priorities in a typical industrial automation project. If you're building something a person has to live with, wear, trust, and rely on, strength alone doesn't cut it, neither does speed. A prosthetic hand that's technically powerful but awkward, unreliable, or numb to feedback isn't a triumph, it's a burden. It has to restore agency, it has to feel responsive and help with actual daily life, not just look good demonstrating capability in a lab. That background shows up in one of the more human details in BrainCo's story. Late in 2025, the company shared the case of a boy named Ma, born with a congenital limb difference, who received a mini version of the BrainCo intelligent bionic hand, custom-fitted, smaller, and lighter, built around real use instead of spectacle. His family talked about it in terms of possibility rather than technical achievement. Swimming, table tennis, a future that opened up a little wider than before. That's not sentimental padding. It's a sign that the engineering culture behind these robot hands was shaped by problems where sensitivity had to come first. Grasping a cup without fear of crushing it, interacting with the world through precision rather than brute force, those aren't afterthoughts in assistive tech. They're the entire job. And maybe that's the hidden advantage. Companies that start out chasing strength often discover control later, almost as an afterthought. Companies that start by solving control for a real human need sometimes stumble into strength as a byproduct of solving the harder problem correctly. That's part of why this hand feels strategically important. It doesn't seem to have started from how do we win a robot demo. It looks like it started from a harder question. How do you make a hand actually useful? Take that route and your priorities shift. You care more about comfort, reaction time, precision, and independent finger movement. You care what happens when the object is soft, irregular, moving, or means something to the person holding it. You care what failure feels like on the other end. Carry that philosophy into robotics, and you don't just get a stronger claw. You get a more thoughtful hand. To see how big that shift is, it helps to remember how rough the history of prosthetic and robot hands used to be. For most of the 20th century, a lot of prosthetic hands were either purely cosmetic or mechanically crude. Some were body-powered, using a harness that translated shoulder or torso movement into opening and closing. Some offered little beyond a hook or a basic pinch. Even once myoelectric prosthetics arrived, reading electrical signals from muscles, the experience stayed limited for a lot of users. The hand might open, close, or cycle through a handful of preset grips, but real tactile feedback was thin or non-existent, so users often had to keep watching the hand to know what it was doing, because they couldn't trust it to feel anything. Delicate objects got crushed. Small ones got dropped. Simple tasks demanded constant concentration. A modern bionic hand with independent finger control isn't just another generation of the same idea. It's a different category of expectation. The gap on the robotics side has been just as wide. For years, the field could build machines that were strong and stupid, or nimble and impractical, but rarely both. Research labs produced beautifully dexterous hands too expensive, fragile, or bulky to actually deploy. Commercial systems mostly went the other way, using simplified grippers because they were cheaper, tougher, and easier to scale. Even now, in 2026, the BBC reported that startups and researchers still see robust, affordable, durable, dexterous hands as one of the hardest problems in robotics. One company cited in that reporting said a more advanced prototype hand could cost around 10 times as much as a simple industrial pincer. Another problem is longevity. A tactile sensor that lasts 6 months might be fine for a research lab, but industry wants something closer to 10 years. That's the part casual viewers rarely see. Building a hand that works once isn't enough. It has to keep working. Durability is where a lot of robotics dreams quietly die. A prosthetic hand already lives a hard life, getting bumped, dropped, sweated on, weathered, used in frustration, used when the wearer is distracted or in a rush. Now scale that up to an industrial setting. Put the hand on a humanoid doing repetitive work for 8, 12, 16 hours a day, add dust, vibration, temperature swings, accidental impacts, and awkward object geometry, and the question stops being, can it do this, and becomes, can it do this every single day, thousands of times, at a cost that still makes economic sense. Claims about mass production stability sound boring next to a viral lifting clip, but in robotics, boring reliability is usually what decides whether a product actually becomes real. Revo 2's documentation reflects that kind of seriousness. It supports SDK integration in Python and C, and it's compatible with Linux, Windows, and ROS. It has OTA updates, closed-loop servo control, custom gesture definitions, and multiple control modes, covering position, speed, current, and PWM. There's a turbo mode based on stall detection that keeps the hand gripping in intervals after a stall, which helps it hold onto soft or shifting objects. Details like that tell you this isn't a concept render. It's a system engineers are expected to program, tune, and build around. At the same time, the limitations matter, and honestly, they make the whole story more believable, not less. This is not a human hand replacement in every sense, not yet. 11 degrees of freedom is impressive for the size, but it's still far from the complexity of a biological hand. Per the published parameter documentation, the current tactile module doesn't sense temperature or humidity, so it can't inherently tell whether a mug is dangerously hot or a surface is wet unless other sensors are added elsewhere. The documentation also notes that startup calibration runs all the fingers through a reset sweep, and if the hand is holding something during that sweep, it can drop it. Small details, but they're the kind that remind you this is a real engineered system with real constraints, not a prop from a sci-fi movie. Oddly enough, that makes the bigger trajectory more compelling, not less, because the field itself is moving fast right now. By 2026, the conversation around humanoids had shifted from novelty toward actual use case pressure. The Guardian reported that Chinese startups were racing to build dexterous robotic hands, since hands are the piece needed to turn humanoids from dancing gimmicks into genuinely useful products, and the same reporting cited Tesla's earlier view that hands make up most of the engineering difficulty, with founders arguing manipulation matters more than walking. One founder called robotic hand design 100 times more difficult than building a humanoid overall, because dexterity is disproportionately hard while the space inside the hand is tiny. That's the industry's nightmare in one line. Maximum complexity crammed into minimum volume, and that nightmare is exactly where value is starting to pile up. Once everyone can buy motors, batteries, chips, cameras, and models off the shelf, the edge shifts to integration. The messy work of fusing mechanics, sensing, control, and manufacturability into something that actually works. A brilliant AI model bolted to a clumsy hand is still a clumsy robot. A less flashy system with reliable dexterous manipulation can start replacing human labor in the spots where traditional automation keeps failing. That's why this corner of robotics matters so much right now. The world doesn't need more robots that perform well on a stage. It needs machines that can handle the weird, boring, irregular work people are constantly asked to do. Restocking, sorting, folding, carrying, cleaning, assisting, assembling, stabilizing, handing over, adjusting on the fly. Think about warehouses for a second. Traditional automation is great when every item is predictable. Same box, same orientation, same path, repeated forever. The moment the world gets messy, mixed items on a shelf, deformable packaging, oddly shaped goods, reflective surfaces, fragile objects, loose cables, partially blocked items, human hands suddenly look a lot more valuable. Workers don't solve every grip mathematically from scratch. They rely on touch, intuition, and quick correction. A dexterous robotic hand with real sensing isn't important because it's elegant. It's important because it targets the exact spot where automation keeps leaking money. Now think about elder care, which is where the emotional and commercial logic really start to overlap. Aging populations in a lot of countries are driving demand for assistive systems that can help with daily physical tasks. And elder care isn't just logistics, it's softness. It's helping someone get dressed, passing objects, stabilizing an arm, adjusting a blanket, guiding a mobility aid, opening a door, maybe eventually helping with hygiene-sensitive tasks where force control matters more than raw strength. A brutal industrial gripper is useless there, even dangerous. The whole use case depends on a machine modulating force within a narrow, safe range while reacting instantly to a human body. A hand that can sense hardness, texture, force direction, and proximity isn't a nice extra in that context. It's the foundation the whole thing rests on. Now think about the home. The dream of a household humanoid has been sold for decades, and most of that dream has been nonsense. Not because robots couldn't walk around a kitchen, but because the kitchen itself is an obstacle course for manipulation. Plastic wrap, soft fruit, slippery dishes, hot mugs, cutlery tangled in a drawer, a damp cloth, appliance buttons, cabinet handles, sponges, pan handles, packaging seals, thin bags, medicine caps, chargers, peels, crumbs, crumpled wrappers, and 1,000 small edge cases people handle without thinking twice. In its launch materials, BrainCo directly frames Revo 2 around future use cases like laundry and cooking at home, and assembly, welding, and inspection in industry. That spread matters because it points to one hand expected to work across wildly different task categories. That's what real utility looks like. Not one tool built for one job, but a single hand meant to cover many. And if you're wondering whether BrainCo sees this as just one hardware product, the 2026 update suggests it's something much bigger. At WAIC 2026, the company didn't just show off a dexterous hand. It unveiled a brain-to-robot AI R&D platform, combining EEG-based intent decoding with robotic execution in under 200 milliseconds, along with an embodied AI data collection system built around a dual arm-wheeled platform, a high-precision glove, and EEG capture from the human operator. In other words, BrainCo isn't only building the hand, it's also trying to chip away at the training data bottleneck behind dexterous manipulation itself. Alongside that platform, the company showed off a new Revo 3 hand with 21 degrees of freedom, full palm tactile sensing, sub-millimeter grasping precision, and 70 newtons of grip force. Revo 2 isn't the end of this story. It might just be the stepping stone. That update reframes everything that came before it. Revo 2 starts to look less like a standalone impressive product and more like one piece of a larger stack. Prosthetics, tactile manipulation, control architecture, data collection, brain signal decoding, embodied AI, and increasingly capable hands climbing from assistive tech into full robotic ecosystems. That's a much bigger story than company builds strong robot hand. It suggests BrainCo already understands something a lot of robotics companies are only now catching on to. The future doesn't get won with one spectacular demo. It gets won by connecting sensing, intention, control, hardware, and data into a single working loop. And the data problem might be even harder than the hardware problem. As Nathan Lapora told The Guardian, hand hardware is improving, but controlling it is a completely different game. Robots need enormous amounts of high-quality data to learn dexterous physical tasks. Language models can gorge on text scraped from the internet. Embodied systems need real-world examples of motion, contact, pressure, timing, slippage, recovery, success, and failure, which is exactly why gloves, teleoperation rigs, tactile datasets, and human demonstration pipelines matter so much. The hardest tasks usually aren't moved from A to B. They're moved from A to B while judging force, friction, compliance, and intent along the way. A robot can see a cup just fine. That doesn't mean it knows how the cup feels in a hand. So when BrainCo talks about embodied intelligence, it's not chasing this year's buzzword. It's aiming at the actual center of gravity in robotics progress right now. Better bodies paired with better training. That's why the company's roots in assistive tech matter as much as its spec sheet. Spend years figuring out how humans signal intent and how a machine should execute a helpful movement, and you end up closer to embodied AI than people who only ever thought in terms of industrial manipulators. Maybe that's the real twist in this whole story. For years, people assumed the road to useful humanoids ran from industry downward. Build machines for factories, toughen them up, then adapt them for homes and care settings later. What if it's partly the reverse? What if some of the most important breakthroughs come from assistive technology first? From the blunt honesty of building for people who genuinely need sensitivity, comfort, natural control, and trust? What if the prosthetic world, precisely because it can't get away with clumsy design, ends up teaching the humanoid world what usefulness actually requires? Look at the design philosophy tucked inside this hand. It's small, it's light, it's fairly quiet, it's protective, it's sensor-rich. It's built to integrate. It comes in tiers, basic, pro, and touch, reflecting different levels of complexity and use. The basic version handles RS-485 and CAN-FD. Pro and touch add EtherCAT for high-speed, real-time communication and broader integration into advanced robotic systems, and the touch version pushes further into tactile adaptive control. That kind of product segmentation says something. BrainCo isn't picturing one monolithic future. It's building a ladder. Simpler applications, more advanced industrial setups, and high-perception use cases where touch itself becomes the whole point. Even the language in the launch materials is telling. BrainCo repeatedly describes the engineering as mimicking the human hand, both structurally and functionally, but frames the goal as performance through efficient design rather than imitation for its own sake, what it calls millimeter-level subtraction, resulting in multiplication in performance. That phrase is a bit much for a product announcement, but it's pointing at something real. Good robotic design usually comes down to subtraction, not addition, less weight, less wasted space, less friction, less noise, less latency between sensing and action, less bulk between actuator and output, better routing, better integration. The payoff isn't just a prettier device. It's a more capable one. Still, it's worth being careful not to turn one strong product into a prophecy. This hand doesn't mean humanoid robots have suddenly arrived. It doesn't mean a home helper is around the corner next month. It doesn't mean every dexterous task is solved, or that hands are now cheap, durable, and smart enough to flood the market tomorrow. The industry still faces real hurdles in cost, control, software training, maintenance, power efficiency, safety certification, long-term reliability, and whether the whole business model even works. The International Federation of Robotics has noted that true multi-purpose humanoids remain a long way off, and even optimistic reporting keeps warning that human-level dexterity is still years away. That caution isn't a reason to ignore what this moment represents. If anything, it's a reason to look closer. Technological shifts often look underwhelming right up until they seem obvious in hindsight. They don't always arrive as one giant leap. Sometimes it's just an uncanny tightening of constraints. Something turns out lighter than expected, stronger than expected, quieter than expected, more integrated than expected. A trade-off that used to be impossible gets a little less impossible. A product category stops looking like a science fair project and starts looking like a supply chain. Years later, everyone talks about the outcome as if it were inevitable all along. Revo 2 has that feeling. Not because it solves everything, but because it solves enough of the right things at once to signal that the field is getting serious. The form factor is serious. The load capacity is serious. The tactile ambition is serious. The interface support is serious. The assistive tech lineage is serious. And the 2026 expansion into data collection, brain-to-robot control, and a higher-end Revo 3 platform suggests the company isn't treating dexterous hands as a dead-end component. It's treating them as the center of a much bigger bet on human-machine collaboration. That word, collaboration, matters. The deepest mistake people make about robotics is assuming the endpoint has to be domination or replacement. The most commercially valuable systems in the near term probably won't be the ones that look the most human. They'll be the ones that fit most naturally into a human world, and fitting into that world means understanding the hand, because the hand is where intelligence stops being abstract and starts being physical. It's where plans run into friction, where intent meets weight, where precision meets risk, where care becomes something you can actually measure. A robot can talk beautifully and still be useless. It can walk elegantly and still be useless. It can reason across enormous datasets and still be useless. But the moment it can reach into our world and manipulate ordinary reality safely, repeatedly, and adaptively, everything changes. That's why a 383-gram hand lifting 20 kilograms matters less as a headline and more for what the headline is hiding. The real story isn't strength, it's convergence, strength converging with lightness, sensors converging with control, prosthetics converging with robotics, human need converging with industrial demand, brain-computer interface work converging with embodied AI. A company that once had to ask how a machine could help one person regain independence is now nudging the whole robotics industry toward a much bigger question. What would it actually take for a machine to work in the human world without being clumsy in it? That's probably the line worth remembering. Not that a tiny hand lifted 20 kilograms. Not the 52.6 grip-to-weight ratio. Not even the tactile sensing or the industrial communication protocols or any of the other specs. The line worth remembering is that one of the most strategically important components in humanoid robotics may have been sharpened not in pursuit of spectacle, but in pursuit of empathy. That changes how you read the whole space. If the best hands are coming from teams that first had to learn what a hand means to an actual human being, then the companies still treating dexterity as a brute force engineering contest might be solving the wrong problem entirely. A hand isn't just a force generator. It's an interpreter, a negotiator between intention and reality. It judges, it adapts, it catches mistakes before they turn into disasters. It handles the fragile and the heavy, the precious and the mundane, the object you barely think about and the one you absolutely cannot afford to drop. That's what robotics has been missing. If that gap is finally starting to close, the implications reach well past one company and one product line. Warehouses get more flexible. Labs get better tools. Prosthetics get smarter. Household robotics becomes a little less fictional. Elder care becomes a little more plausible. Humanoid platforms stop getting judged only on how they move and start getting judged on whether they actually contribute. The future of robotics may not belong to the machine that looks the most alive from a distance, but to the one that can touch the world most intelligently up close. So yes, a tiny human-shaped hand lifting a massive weight is an impressive image, but the more you sit with it, the less that image feels like the actual point. The point is that this hand didn't start as a stunt. It started as an answer to something missing in someone's life. And now, in one of those turns history seems to enjoy, the technology built to restore something deeply personal may end up helping crack one of the last genuinely hard problems in robotics. A hand light enough to seem delicate, strong enough to seem impossible, sensitive enough to tell a matchstick from a metal weight. Engineered not just to grab, but to feel. Born out of prosthetics, moving into humanoids, now expanding into brain-to-robot systems and richer embodied AI pipelines. That's not just a better robot hand. That's a preview of how the next real generation of robots might actually become useful. And if that future shows up sooner than people expect, don't be surprised if the breakthrough didn't start with some giant machine in a giant factory, but with a smaller, quieter idea that before a robot can really work like us, it might first have to learn what it means to hold the world the way we do.